Hey guys, welcome to the lesson on linear models. So a linear model is a model that represents quantities that increase and decrease by a constant amount over equal intervals. And we're going to look at a couple different examples today and how we can tell whether it's a linear model or not a linear model. So in a table of values, the first differences are always equal, and I'll show you how that works in one of the examples. The graph is always a straight line, so it can be pointing up or down or to the side. The equation of the line can be written in the form y equals mx plus b. So you've probably seen this before in your grade 9 or 10 math, where m is the slope or that rate of change, so we already know how to figure that out. That's the rate of change. We did that in the previous lesson. And b is the vertical intercept, which is where it intercepts on that y-axis. And the rate of change is constant. And like I said, the rate of change is our slope. So they mean the same thing in this case. Let's look at the example and we'll go over a couple different ways that you can check to see if it is a linear model. So, which models represent linear relations? And we're going to justify our answer. So I'm going to go through each one and we'll look at why it's not a linear model. So the first two are little graphs. And what you're going to do is you can find the first differences. So if the first differences are the same, now all that means is you're going to take the dependent variable, so the variable that you would put on the y-axis, and find the differences between them. So the first one, we have 60, 55, 40, and 15. And the one to choose is usually the one with time is something that's consistent and goes up at the same time all the time. The other one might not be. So that's usually the one I choose. So when you do the differences, you're just going to subtract one from the other. So the difference between 60 and 55 is 5. Between 55 and 40 is 15. And between 40 and 15, the difference is, oh my god, my math, 25. Now notice they're not the same. Not the same. So we can say that this is not linear. So that was for A. B, we're going to do the same thing. What I wrote there. B, we're going to do the same thing. So I'm going to do the earnings, which goes from 0 to 40 to 80 to 120. Now it's quick to see that the difference between this is 40, 40, 40. So since these are the same, I can say that this one is linear. So we can go, yay, it's linear. On a graph, so that's how you kind of deal with the table of values. You just look at those first differences. When we're looking at graphs, so we'll do C and D. Notice in C, this is a straight line. It doesn't have any curves to it. It just goes in the downward direction, but it is a straight line. So right away, I can just look at it and C is linear. And you can say, because the graph has a straight line. Easy as pie for that one. D, which is our other graph, notice how on this graph it starts off slow and then goes up, and it has a curve to it. It's not a straight line. So for that one, we can say it's not linear. And then I might say why, and you can say because it's not a straight line or it's a curved graph. Any one of those reasons is enough to say it's not linear. The last one, E and F. Now, when you are looking at these, they have to look like, when you're looking at the equations, they have to look like y equals mx plus b. Or another kind of thing to look at is on the x variable, the x has exponent of 1. So it's not a 2, it's not a 3, it's not anything crazy. It's just, it doesn't have anything on it. There's no exponent on the x, because 1, they just leave it off. It's just it doesn't have anything on it. So e is in the form of y equals 2x plus 5. So here's our m and our b, and our x doesn't have any exponent on it. So it is linear. F looks like this, x squared plus 5. Now notice this one is not linear because it has, let me use a different color. It has this exponent here. That's a 2. Because it has a 2 means it's not linear anymore. So for this one, I'm going to say it's not linear. So those are the differences. You have to look, if you have given a table, do those first differences, find out what are the differences between all those y values. If they are the same, then they're linear. If they're not the same, then it's not linear. Look at the graph. Is it a straight line or not? If it's a straight line, then yes, it's linear. If it's not a straight line, it's not linear. And then look at your equation if you're given an equation. So if it looks like that y equals mx plus b in any way, then you can say yes, it's linear. And if it doesn't look like that, if the x has any sort of exponent that's greater than 1 on it, then you can say, nope, it's not linear and I'm moving on. Let's go to the next page and we'll look at a different example. And I've put a note at the beginning here. In real world graphs of linear relations, the vertical intercept represents the initial value of the dependent variable. That's our y-intercept. And the slope represents the rate of change in the dependent variable with respect to the independent variable. I kind of went over that at the beginning, but now we have it like in words. We can compare the graphs of pairs of relations to investigate how the initial value and rate of change are reflected in the graph. Let's compare pairs of linear relations. A cup of coffee is reheated in a microwave. The temperature, C degrees Celsius, of the coffee after T seconds can be modeled by linear equations. 500 watt power setting has it as C equals 0.5 T plus 20, and the 1000 watts power setting is T plus 20. Explain what the numbers in the equations represent. And then B, we're going to graph both equations on the same axis. How are the numbers in the equation reflected in the graph? Okay, so let's look at A first, and we'll talk about what are the numbers in the equations do they represent. So remember I said if it's linear, it looks like this. Y equals mx plus b. And then let's look at our two equations. The first one is C equals 0.5 T plus 20. And the 1000 is C equals T plus 20. Now notice that this is like mx. Hold on, I'm going to do that in a different color. Just so it looks. So this was m. That could be our x and b. And in this case, we have an m, which it's not there, so it's a 1, x plus b. So we know they're linear, but what does that really mean? So the m, so in this one, our slope or rate of change is 0.5. And in this one, our slope or rate of change is equal to 1. So if you want to talk about which one, what the slopes are doing, this one here has a bigger slope because it's 1 and this one's only 0.5. So it's going to go up slower. The other thing The 20, what does the 20 represent? So in this one, this is the y-intercept is 20, which is also our initial value. So it's where it starts. And in this one, our initial value, or our y-intercept, is also 20. So what does that tell you about these different equations? They both start at the same spot, but they have different slopes. So that should be reflected when we do our actual graphs. So part B said graph both equations on the same axis. How are the numbers in the equation reflected in the graph? So I went to Desmos and I did a graph, and I have a copy of it, and I'm just going to paste it in here. So just one sec, guys. All right, so here is my graph. Oh my goodness, I don't want to do that. Hold on. Here's our graph. I went to Desmos and I grabbed it, so then I put it into here. But if you go to Desmos or you want to do this by hand, it doesn't really matter. There's what the graphs look like. Notice, here's where they started, right at 20. And notice that the first one, which was the 0.5, that's our red line. I'll label them, sorry guys, 0.5 t plus 20. And then this one was the t plus 20. The red one, I said, has a slower rate of change. So notice that it doesn't go up as fast as the other one. If you want to, if this was a pricing thing and you were paying, what are we actually doing? Power setting, reheat in a microwave. So if I wanted to know which one's going to heat it up faster, then I would say that blue one is faster because the slope is faster. And notice how the temperature rises a lot quicker. If you wanted it to heat up more slowly, then I might choose the one with the power setting of 0.5 plus 20. So that's kind of like the steps, or what you kind of have to think about when you're looking at the different linear examples. If it ever tells you to graph, go ahead, guys, use Desmos. It's nice and easy rather than doing it by hand. But those are the kinds of things you're going to be looking for. Is it linear or not? Finding the first differences, looking at the graph or looking at the equation, and then comparing the equations. And you can graph them to compare them if you want. It's really up to you. But that's it for today, and I'll see you guys later.